Good morning, students. Welcome back to science class. Today we shall start new chapter, that is energy, work and energy. Okay. See, in the two previous chapters, in the first chapter we had studied about the distance, displacement, and velocity, how the object is moves, whether the object is slow or speed, and also we proved equivalent derivations for the equations of motions. Okay. In the second chapter, we had discussed the cause for the change in velocity, correct? So, because of the application of force, we can change the velocity of an object. mm, we can change the direction of an object. We can bring objects from rest to motion or motion to rest. And also, we had studied three important laws. Okay, those are Newton's laws of motion. Okay, so if one object is at rest, it remains at rest only. If one object is in motion, then it remains in motion only when in the absence of external force. Then also we had studied the so what F is equals to ma, that we can calculate using that formula, that applied force. Okay, and in third law, we had studied to every action there is equal and opposite reaction. At last we had studied the conservation of momentum. Okay. So now we shall start work and energy chapter. Okay. See, take a bus. Okay. So bus, it carries more than 50 people at a time. But take one more, take a cycle. Okay, it can't carry 50 people. Maximum it can carry 2 or 3 people. So what is the difference here? So here, that bus, it will do lot of work, but that cycle, it will do very less amount of work. Why? If you want to apply a force on an object, then you need something. So what is that? Okay, so if you want to apply a force on any object, you need energy. Okay, so here that bus, it has more energy compared to that one cycle. So that's why that bus, it carries more than 50 people, and that cycle, it carries only 2 or 3 people. Okay, so to apply a force or to change the state of an object, you have to apply a force, right? If you want to apply a force, then you need energy. Okay, so without energy, you can't do you can't apply any kind of force. Okay. Then okay, so before discussing about energy, we will discuss work. Okay, see, work means what? If you want to apply a force, then you have to do a work. So how you will do that work? If you have energy, then you can do work, otherwise you can't. In our normal, okay, in our common language, for example, I will say to one student, go and bring one chalk. Okay, so he will bring that chalk and give it to me. So then we can say that the work is done, because I have told him I'm going to bring that chalk, so he will bring that. So we'll say that work is done. And no, in your family, for example, your parents, they will say that go and bring 1 liter of milk. So you will go to the shop and buy 1 liter milk, and you will give it to your parents. Okay, so at that time we can say that work is done. Okay, and for example, from morning onwards, okay, you will do lot of work from morning to evening. Okay, if that work is complete, we can say that yes, the work is done. Do you think that the meaning of that work done in science also same, means in our common language and the science? Okay, see, there is a different meaning about work done in our common life and in science. Okay, for example, say, just imagine, from morning onwards. Okay, from morning onwards, you are pushing this wall. Okay, you are pushing this board up this wall. Okay, it doesn't displace its position, it stays here only. That's why it is stick together and it is wall, right? Okay, so we can say that hey, he's from morning onwards he is doing that work, but in science we can't will say that work is not done. Okay, but we use that word, what he is doing from morning onwards, he is trying, he got exhausted, we will say like that. But in front of science, we can't say that work is done. Okay, yes. Before that, why we need energy actually? Yes, for us we need energy to do a lot of work. Okay, a lot of work means what? We have to carry the bag, school bags, we have to write, we have to read, we have to play. For that we need energy and we have to do some other works. Okay, then for animals also they need energy, right? Why? Because they have to perform a lot of activities. Okay, for example, say they have to escape from enemies, they have to for search food, they have to live for safe places. Okay, they will find safe places to live. Okay, even animals also they need energy. Okay, now how when do you say that work is done? Okay, in science, when do you say that work is done? Okay, say in our common language we'll say that, already I told, right? If I say that one student go and bring one chalk, you will bring that chalk, so we will say that work is done. But in science, when do you say that work is done? Okay, see here, if you want to say work is done, if you want to say work is done in science, so here two conditions are very important. One, the application of force and displacement of that object. For example, see here, now this is a marker. I will apply a force. Now see, this is the position of the marker here. I will apply some amount of force. Okay, so after the application of force, it displaces its position, or say it covers some distance, or it will move, and it will move and it covers some distance. At that time only we can say that work is done. Clear? If you want to say work is done in a science, that object it should displace us from its original position. Means if you want to say work is done, so here you have to apply a force. If it displaces its position or if it covers some distance after the application of force, then we can say that work is done. Okay, say for example, one student, from morning he will say he will wake up from morning and he will read and write and he will go to school. While going to school he will carry some of books and lunch box. Okay, there also they will listen what the teachers will explain. Okay, they will write, they will summarize everything, and once again she will come back to evening. Once again she will read and write, she will play with the friends. Okay, and she will do some other works. Okay, from morning to night. So we can say that yeah, she has done what lot of work, she will do lot of work like that. Okay, but in science that is different. Clear? In science field, when we say that the work is done, when the object covers some displacement after the application of force, then we can say that work is done. Okay. For example, say here, just see here. You know, just like this is a table. Just imagine this is a table. Okay. Here one marble is there. Here one. So you will apply a force. Apply force means what? You will push that marble. You will push that marble. Okay. So what will happen? So it starts to move. Say it will cover some distance. Okay. It stops here. It will cover distance here. Okay. Here why that marble got displaced? Because here we have applied a force. So that's why it got displaced. It is moved. Okay. So here the force is applied and it covers some distance. So here we can say that work is done. Okay, here we have applied force and it covered some distance. So here we can say that work is done. Okay, now second situation, say one girl is pulling a trolley. Okay, just imagine one girl is pulling a trolley. What will happen? She will apply a force on that trolley. What will happen? That the trolley it will cover some distance. Okay, there also that girl applied a force and that trolley got moved. Okay, means that trolley covered some distance. So at that time also we can say that work is done. Okay, next say take one more example. Lift a book. Okay, see here. Okay, so now this book is here. Okay, I will lift this book up to here. Okay, I will lift this book up to here. Clear? So now here I apply. See, if you want to lift this book from here to here, here you have to apply a force, right? So without force, it can't move. because already we are studying the second chapter. If one object is at rest, it remains at rest only, or if one object is in motion, then it remains in motion only in the absence of external force. So that's why now this book is at a state of rest. If you want to change its position, then you have to apply a force, right? So when you apply a force, then only we can lift this book, or if this book rises here. So here also we have, see, here also I have applied a force and it covered some distance. Here it covered some displacement. So here also we can say that work is done. See here we have discussed three examples. One is this marble, second one is that girl, she pulls a trolley, okay, and here we lift that book. Clear? In these examples, if you notice, there are two conditions are necessary. Okay, in these examples, two conditions necessary. See here, one is force, second one is displacement. Okay, so in the first case, here the force applied on the object, that object got displaced and it got some displacement. So your work is done. In the second example, one girl, she pulled a trolley. That trolley also got displaced. Okay, so we can say that due to the application of force, that trolley covered some distance. So there also we can say that work is done. And in third example, so I lift that book. So there also, because I applied a force on that book and that book got some distance and some displacement. So there also clearly we can say that work is done. Okay, if you want to say work is done in science, there are two conditions are necessary. That is one force and another one is displacement. Okay. See here, if any one of these two conditions, if it does not exist, okay, if any one of the condition does not exist, either force or displacement, okay, either force or displacement, then we can't say that work is not done. For example, see here, just imagine I am applying a force on this wall. The wall is not moving, right? It doesn't displace its position. Okay, so then we can say that work is not done. See, you from morning onwards, you are pulling that work. Sorry, you are pulling this wall from morning 10 o'clock to evening 4 o'clock. Okay, you'll pull that wall. If that wall doesn't displace its position, then we can say that work is not done. So if you want to say work is done in a science, so here you have to apply a force on an object, then that object should cover some displacement or it should displace its position. So then only we can say that work is done. Okay. Yes. Next. See here, how to calculate that work done. In the previous classes, in the previous chapters we had studied, right? So we can calculate that applied force using the formula F is equals to m into A. If you know the mass of the object and its acceleration, then we can calculate that applied force. Okay. So now see here, how to calculate that work done. Here, if you want to calculate that work done, here, if you want to calculate that work, if you want to say work is done in science, there are two conditions are necessary. One is force, another one is displacement. Okay. See here, we use capital W. We use capital W to represent work done. Okay. So to calculate work done, we know the formula, that is force into displacement. Force into displacement. Okay, force into displacement. In short form we can write, so W is equals to force into displacement. Okay, for example, if you want to calculate the work done on an object, if you know that applied force, and the displacement covered by that object, okay, so then we can calculate work done. Okay, now what is the SI unit of work done? What is the, yes sir, good morning all. So now no need to say good morning. Okay, if I ask any questions, just answer it. So now don't send simply good morning, good morning. Okay, yes, see here. Now tell me. So now put answer in the comment box. So what is the SI unit of work done? We know the formula. Work done is equals to force into displacement. So now tell me, what is the SI unit of work done? Quick. What is the SI unit of work done? Yes, here Shruti and Channu partly answered. Yes, in Joule. So before that Joule, one more or one more is there. Okay. Yes, what is that? Yes, Joule, correct. Okay. So one more is there. Instead of that Joule, we can use one more assignment. Yes, that is Newton meter. Okay. We use Newton to measure the force, and we use meter to measure the displacement. So that is why the SI unit of work done is Newton meter. Instead of that Newton meter, none of that scientist. Okay, so we use Joule. Both are same, Newton meter or Joule. Okay. Yes. So now already I can say in your previous year in 8th standard you had studied, okay, about the work done. Clear? So now tell me. Say I will say 1 joule of work is done. 1 joule of work is done, or 2 joule of work is done. So what is the meaning? 1 joule or 2 joule or 3 joule? Yes, please define or please tell me what is the meaning of 1 joule of work is done, or 2 joule, 3 joule. Quick. Here, Varun Kumar, you answer Newton per meter. It's wrong. It's not Newton per meter. Okay, it's a Newton meter. Please correct it. Okay, it's not Newton per meter. It's Newton meter. Yes. Now tell me what is the meaning of 1 joule or 2 joule. Quick. Yes, here Channapatli answered 1 Newton force is applied on an object covers a 1 meter of displacement, then it is said to be 1 joule of work is done. Yes, very good. Okay, if you want to say 1 joule means, so here if you apply 1 Newton force on an object, if you apply 1 Newton force on an object, if that object, if it displaces for 1 minute, sorry, 1 meter, or if it covers 1 meter distance, then we can say that 1 joule of work is done. Okay, see here one object is there. Okay, so here you will apply 1 Newton force. 1 Newton force. If it covers 1 meter distance, 1 meter, 1 meter distance, so then we can say that what 1 joule of work is done. Okay, now tell me what is the meaning of 5 joule of work is done. What is the meaning of 5 joule? What is the meaning of 5 joule? Yes, Sangeeta, you answered the work done with 1 Newton and 1 kg. What is that 1 kg? It's wrong, completely wrong. Okay. And Varun Kumar Angadi. So here you have sent Newton per meter. It's wrong. It's not Newton per meter. It's Newton meter. Okay. Because here force into displacement. It is not. Suppose if it is a force by displacement, yes, Newton per meter is correct. Okay, so its formula is force into displacement. So that's why it is force into Newton in Newton meter. Yes. Now tell me, what is the meaning of 5 joule? Yes, the 5 Newton force is applied on an object which covers a 5 meter. No, it's wrong. Why? Because see here, 5 Newton force into 5 meter. Then answer you will get 25 Newton meter or 25 joules. It's wrong, right? Yes, see here. Okay, now tell me. I'll wait for your answer. Fast. So, what is the meaning of 5 joule? What is the meaning of 5 joules? Quick. See, just observe this formula. According to this formula, tell me, it's very easy. If 5 Newton force applied to an object, if it covers 5 meter, no, it's wrong, Nitin Kumar. And the object is 10 kg. No, it's wrong. Why are you using that 10 kg? Here we don't want that mass, right? We know the formula only what for work and equal to force into displacement. If 1 Newton of force is applied on an object, if it covers 5 meter, yes, now the answer is correct. Yes, 5 Newton with 1 meter displacement. Yes, even that is also correct. See here, if you apply 5 Newton force, if the object covers 1 meter distance, okay, if the object covers 1 meter distance, so then we can say that 5 joule of work is done. Or if you apply 1 Newton force, if it covers 5 meter distance, then also we can say that 5 joule of work is done. Now tell me, what is the meaning of 10 joules? Now tell me, what is the meaning of 10 joules? Quick. Yes, so 5 Newton with 1 meter displacement, 5 Newton with 2 meter displacement. Yes, 5 Newton with 1. Yes, correct answer. So 5 meter force is applied on an object covers a 2 meter of displacement. Yes, see, you can define this 10 joules in many ways. Okay, first one you can say, say here 10 Newton force applied, and if the object covers 1 meter distance, so then we can say that 10 joule of work is done. Or if 1 Newton force applied and it covers a 10 meter distance, so then also we can say that work 10 joules of work is done. Or if you say 2 Newton force applied and that object covered 5 meter distance, so then also we can say that 10 joule of work is done. Or you can say that 5 Newton force applied and that object covered 2 meter distance. So at that time also we can say that 10 joule of work is done. Okay, hope you clear what is work done. Okay, so when do we say that work is done in a science? If you apply a force on an object, if that object covers some distance, so then you can say that so work is done. Okay, so now tell me which quantity it is work done. So here force is vector quantity, displacement is also vector quantity. Then work done, whether it is a scalar quantity or vector quantity. Yes. So work done, whether it is scalar quantity or vector quantity. Tell me which quantity it is. Faster. Yes, it is a scalar quantity. Channu Patil. Yes, why? Give the reason. Yes, a scalar quantity, correct. Give me the reason. Why it is a scalar quantity? First. Why it is scalar quantity? Because it has only magnitude. How do we say that it has only magnitude? You know, if you apply a force, correct? See, for object is here. If you apply a force, then that object will move in this direction, right? So here, force it has direction and magnitude. Displacement it has both direction and magnitude. Okay. See here, yes, your answer is correct. What work done is it's a scalar quantity. Why? Because see here in higher classes you'll study that the product of two vectors which gives scalar. Okay, the product of two vectors which gives scalar. So this is the mathematical meaning. See, theoretical meanings. Okay, yes, the theoretical meaning means, you know, right? If you want to say 2 joule, see how much amount of work is done, you need just 2 joule of work is done. Here, you to understand that one, you don't need any direction. Okay, if you want to understand that work done, just you need one number, right? 10 joule of work is done, or say 1 joule of work is done. So here you will understand that 1 Newton force applied and that object covered 1 meter distance. So here you need just one value, magnitude. Here to understand that work done, you don't want direction. Correct? So that's why work done is a scalar quantity. Okay? Yes. So next one, see here. You know, just imagine one object is moving in this direction. Okay? One object is moving in this direction, but you will apply force in this direction. Okay, so at that time, so this object also it covered some distance, finally it will come to rest. The object is moving in this direction, you will apply force in this direction. So now tell me, in this case, here is it possible to calculate work done? Is it possible to calculate work done? Here, object is moving in this direction, and here you are applying force in this direction. Okay? Yes, it will come to finally it will come to rest. Why? Because here you have applied a force. Okay? Yes. Now tell me, in this case, here work is done. So when do you say that work is done? Here you have to apply force. So force is applied. If that object got some distance, then we can say that work is done. So here also, here you have applied a force and that object covered some distance. So clearly we can say that work is done. Okay? But here, in this case, here we will say that work done is negative. In this case, work done is negative. Why? Because here that object is moving in this direction and that object covered some displacement in this direction. Okay, but here the applied force is in this direction. So that applied force and displacement both are opposite. Okay, so that's why here we can say that in this case we will get negative work done. Okay, if the see when you apply a force against the direction of the object, at that time you will get negative work done. For example, one object is moving in this direction, you will apply force in this direction also. So at that time you will get work done in positive. At that time you will get positive work done. Suppose if the object is moving in this direction, if you apply a force in this direction, okay, then that object will cover some displacement in this direction. So at that time we can say that we will get negative work done. So clear, right? When do we say that a negative work done, positive work done? Okay, if both displacement and applied force, if both are in same direction, then we can say that work done is positive. If both are opposite to each other, then we can say that work done is negative. Okay. Or see one more example. So now this marker is at rest. Okay, so here I will apply a force in this direction. So now here it will cover in this. So now here we can say that this here work done is positive, because initially this object is at rest, right? So you will apply force in this direction, and this marker will cover some displacement in this direction. So that's why we can say that work done is positive. Okay. Yes, next one. See here. So now there's a small problem. Okay, we'll discuss it. Yeah, a porter. Yes, see here, one small problem. Porter lifts a luggage of 15 kg from the ground and puts it on his head 1.5 meter above the ground. Calculate the work done by him on the luggage. So here calculate the work done. Okay. Yes. See here. To calculate work done, we know the formula, that is W is equals to force into displacement. Force into, right, to represent displacement. Okay, work done equal to force into displacement. And here say they have given mass. M is equals to 15 kg. Okay, to calculate work done, we need force and displacement. Here they have given displacement, that is 1.5. So S is equals to 1.5 meter. But we don't know force, right? But how to calculate if not force? When we know the formula, that is F is equals to M into A. Here given mass, that is 15 kg. Then what about A? So here acceleration is equals to, we can take 10 meter per second square. 10 meter per second square. Okay. Actually that value is 9.8 meter per second square. Okay. So you will study why that 9.8 meter per second square in the gravitation chapter. Okay. So here A is equals to 10 meter per second square. You know, right, while falling and going upwards, the accelerator always will take the acceleration equal to 9.8 or 10 meter per second square. Okay. Yes. So now here this is 10. What is the answer? That is 150 Newton. Now substitute here. So 150 into 1.5. 150 into 1.5. So here we will get 225. Okay, 225 joules. 225 joules. Okay. Yes, here the answer is 225 joules. Correct. Okay. Yes, I will stop here. So tomorrow I will continue the class. Thank you.